So we've talked about this anticoplanar arrangement of our leaving group and our hydrogen that we are picking off. So if I just take tert-butyl bromide, we would draw the mechanism for an E2 reaction. Let's use sodium methoxide as our base. We're going to pick up this proton, make a double bond, and kick out our leaving group. Now, the key here is that this hydrogen carbon-carbon bromine arrangement needs to be 180 degrees and needs to have a dihedral angle of 180 degrees. And we've talked about this before, but in this video, we're actually going to look at some practice problems. You guys have told me you like when I do practice problems, so consider this like an extra video on top of your normal lecture videos, so that way we can dive into topics in particular. All right, so when do you need to watch out for this anticoplanar rule? And the one I showed you before, it didn't really matter because this methyl here has other protons that you could pick out, okay? So this one, well, we draw it as if this is anticoplanar, but any three of those protons can be used. We can rotate that single bond. So this is becoming really important for three different cases. The first one is if both the alpha carbon and your beta carbon are chiral. This is going to give you two different alkenes. So it's important that we set this up correctly in this anticoplanar fashion. The second one is if both the alpha carbon and your beta carbon are in the same ring. Let's do a practice problem together. And in this practice problem, we're going to have our alpha and our beta carbon be chiral. We're going to look to see how this anticoplanar business is involved. So in this case, both our alpha carbon and our beta carbon are chiral. Let's label them. We're going to do this reaction with sodium methoxide. And we'll label these here. This is our alpha carbon, and our beta carbon of interest is this one. Now we know we have one more beta carbon here, but we've talked about how the most substituted alkene will be favored. So this beta carbon here on the internal side of this molecule is going to give us the most substituted alkene. We can label our chiral centers here with this little star here. And if we look at R and S, we can look at the beta carbon here and see that we have priorities of 1, 2, 3, and the methyl is 3, and the proton there is back. And this gives us an S. Okay, so the beta carbon is S in this example. I'm going to erase these now. And if we do the same for this alpha carbon, you might want to pause the video and see if you can figure out the R or S for this. And I will tell you that this is, there's a proton here, okay, priority 1, 2, and 3. Okay, we can use an arrow here showing it's going to the right or clockwise. That would mean that stereo center at the alpha carbon is an R. Okay. Pause the video and try it again if you had any issues with that. So when we're looking at this, we know that when we do the E2 reaction, we need to have the proton and the bromine here, our leaving group, we need to have them anticoplanar. So what we're going to do is we're going to reorient this molecule and rotate it. We're going to rotate this molecule so the proton and the Br are in fact anticoplanar. I'm going to take this whole side of the left of this molecule and rotate that carbon. You might need to build a model kit if this gives you any trouble. And honestly, when you first start with organic chemistry, building model kits, you won't have to do it all the time, but eventually it just starts to click and make sense. So if I rotate this, I'm rotating it towards me. Actually, this ethyl group will now be coming towards us. And then the methyl that was there is going back, and the proton is now in the line form. And one of the ways you can see it too is that you switch all of these one position, okay? So just make sure, we can also go in and just make sure that we do have an S stereo center still, okay? So this would be 1, 2, and 3, okay? And so if I try to use my right hand, it doesn't work, but if I use my left hand, proton is my thumb, my fingers are at the 1 position, and I rotate them, it goes 1, 2, 3. So cool, we still have an S, which is awesome. So that's one way to check to make sure you rotated it correctly. So let's draw our mechanism here. And you're going to see quickly why we need to draw this mechanism and why we need to rotate it really for this anticoplanar. This is anticoplanar. Notice here we're going to make this alkene, right? This arrow, here's our arrow 1, and here's our arrow 2. The second arrow is making that double bond, and then our third arrow is kicking out the bromine. I want to ask you a question. What is the relationship between the two methyls of this alkene? Are they on the same side or opposite sides of the alkene? They are on opposite sides. One is a dash, one is a wedge. Okay, so when we draw our alkene, you can draw your alkene first. We know we have one of the methyls here, and one of the methyls is opposite of it. If I label my carbons, I'll do it in purple here, the alpha and the beta carbon, okay? If I say this was my alpha and this was my beta, on the beta carbon, we have 2 groups. We have a methyl group and an ethyl group. It might be worthwhile for us to pause the video and count your carbons, okay? I'll do it with you. 1, 2, 3, 4, 5, 6, okay? So we're going to find those 6 carbons on our starting material. So here's 1, 2 is our alpha, cool. 3 was our beta, okay? 4, 5, 6. Cool, we have all of our carbons. This is one way to kind of keep track of everything. And we have a alkene here that's tri-substituted. Now, you could draw another substitution pattern for this. Where the 2 methyls are on the same side. Let's ask ourselves, is this E or Z? So the blue one here, let's look at this. Dotted line down the middle. When we look at the right side, the methyl wins, okay? So this side, the top side wins. And when we look at the left side, the ethyl wins. So this would be a Z alkene. Now, when I look at this green alkene, the methyl here on the left wins and the ethyl wins here on the right. So this would be an E alkene. This one does not form. This is because we need this anticoplanar relationship between our hydrogen and our leaving group. Let's look at this again. So the 2 methyls, when we rotate this molecule to put the hydrogen and the bromine in a 180-degree dihedral angle, check out the relationship between the 2 methyls. They are opposite of each other. One is dashed and one is wedged. The alkene where both of the methyls are on the same side does not form because we would have to adopt something that isn't anticoplanar. In fact, I'll draw it below. In order for this green one to form, this E alkene, we would have had to adopt the hydrogen and bromine on the same side. Now, if I rotate the molecule here, okay, there's our methyl, and the bromine side I've rotated. So now I've pulled it up to the front, and so my methyl here is going back, and then I just have a hydrogen on this side. So this is what it would look like, and both of the CH3 groups are on the same side. We could then do our E2 reaction, but this is not anticoplanar. So this is why it's super important. When you have an alpha carbon and a beta carbon that are chiral, you have to rotate it and make sure before you draw your alkene product, because in this case, you only get this alkene as your desired product. And I just want to make one more note on here. In good old organic chemistry fashion, we are learning that the syn orientation of our hydrogen with our leaving group does not undergo E2, okay? However, guess what? Not in this class, but you will learn one reaction in your next organic chemistry course that there is this syn elimination that can occur, but don't do it. It's not in this course, so don't worry about it for right now. It takes a lot more forcing conditions, okay? So in this course, syn, no. It takes really forcing conditions because the orbital overlap is really bad, okay? So just know that in good old orbital overlap, bad orbital overlap, just know in good old organic chemistry fashion, things that we try to make rules about, nature's like, haha, there's actually ways around this. And with really forcing conditions, you can actually do an elimination here, syn, but we won't be doing it in this class. So no funny business with this. Has to be anti-coplanar, just like we've talked about. They learned E2. Anti-coplanar. That's a good high five, Rhodey. High five. Yeah, they did it. Woo. I've got another video with rings coming up.